Good morning, all of you. Welcome to Sri Jayendra Rank Zone. In the previous lecture, we have completed geometrical isomerism as well as isomerisms based on structural isomerism, that is linkage isomerism, ionization isomerism, etc. Now, in this lecture, we are going to discuss optical isomerism, that is another part of stereoisomerism. And in the previous lecture, we have done up to geometrical isomerism. Now, in this lecture, we are going to learn about optical isomerism as well as questions related to isomerisms and awareness theory. So please listen carefully. This lecture is very important. From this lecture, you're definitely going to get one question for entrance exam. So what I'm writing on the slides, you have to write in your classwork. Apart from that, whatever slide you're seeing on the screen, you should note down in the classwork immediately. Then only you can understand it better way. So please do it immediately. Thank you. Now we are continuing with this lecture number 3, that is coordination compounds. So in the previous lecture, as I told you, already we have done up to geometrical isomerism. Now we will start with optical isomerism. It is another type of stereoisomerism. Optical isomers are the mirror images that cannot be superimposed on one another. These are called enantiomers. The molecules or ions that cannot be superimposed are called chiral molecules. The total molecule is called as chiral. The two forms, dextroform and lavoform, are defined depending upon the direction they rotate the plane of polarized light in a polarimeter. So, if the molecule rotates the plane of polarized light towards right, it is called dextro. And if it is rotating towards left, it is called lavo. Just like the same thing we are observing. So right form, so left form it is dextro form, and right form it is lavo form. So if it can have the, it is, if the molecule is having the potentiality to rotate the plane of polarized light towards left or right, towards left it is dextro and right towards it is lavo form. So optical isomerism is common in, very important point, please note on here. Optical isomerism is common in octahedral complexes involving bidentate ligands. Definitely it should have one bidentate ligand. The minimum condition is the complex should contain at least one bidentate ligand. It can consisting of 3 bidentate ligands or at least one bidentate ligands and 4 different ligands. So please note down, this is very important. So the optical isomerism is common in octahedral complexes. Geometrical isomerism is common in square planar complexes as well as octahedral complexes, but optical isomerism is common only in octahedral complexes involving bidentate ligands. So this is very important point. Please note down, children. It's very important. Optical isomerism is common only in octahedral complexes involving bidentate ligands. Bidentate means it can donate 2 electron pair. How many electron pairs? It can donate 2 electron pairs. 2 electron pairs, which can, the ligands which can donate 2 electron pairs are called as bidentate ligands. So which type of compounds will show optical isomers also I'll write here. So please note down. Let us see the example of optical isomerism. So the first condition is the molecule should possess octahedral complex. Second condition is it should involve at least one bidentate ligand. That is more important. So example here, this is dextroform, which can rotate the plane of polarized light towards left. And here the left is En. En is called nothing but ethylene diamine. It is bidentate ligand. So COEN taken twice. This is a molecule COEN taken twice. COEN taken thrice. Charge is +3 here. And this is also same. But here it is rotating the plane of polarized light towards right. So En is coming right and left. This is dextroform and this is lavoform. Left to right. So dextroform and lavoform. So please note down. Next continuation. So has dextroform as well as lavoform in a coordination entity of the type PtCl2En taken twice. As I told you, this is one bidentate ligand and 2 monodentate ligands. Total it comes around 6 +2 charge. Only the cis isomer will show optical activity. This is the form molecular Ma2B2. Ma2B2 +2. M is called central metal atom. A is called monodentate ligand, twice are there. B is called bidentate ligands, twice are there, +2. This will show as well as geometrical as well as optical. This compound is very important. It can show geometrical as well as optical isomerism. So this is nothing but optical isomerism. So which type of compound will show optical isomerism? I'll just write it here. Which type of compounds will show optical isomerism? Please note down. The compounds So before going to this, I'll write here the compounds which can show optical isomers. Please note it down. It's very, very important. The compounds are the molecules. The compounds are the molecules with octahedral complexes which have octahedral complex which have octahedral complexes octahedral complexes which have octahedral complexes with general formula with general formula. This is very important, children. Please note it down in your classwork with general formula M A2 B2 C2 whole to the power plus or minus n. This will show geometrical, and the cis isomer of this will show optical. Cis isomer, as I showed you in the example, cis isomer will show optical activity, So please note down, this is very, very important. Next, M A2 B2 CD whole to the power plus or minus n. Next molecule M A2 BCDE. This means total 6 ligands, total 1 plus 4, 5 ligands, but this is monodendritic ligand having 2 plus or minus n. And finally M A B C D E F also will show can exhibit optical activity. So which type of compounds will form optical isomerism, will show optical isomerism or optical activity? The compounds having octahedral complexes with general formula Ma2B2C2 plus or minus n, Ma2B2CD plus or minus n, Ma2BCDE plus or minus n, and MABCDEF plus or minus n can exhibit optical activity. And one more important, it should contain at least one bidentate ligand. It should contain at least one bidentate ligand. So bidentate ligand means which are having the capacity to donate 2 electron pairs. Bidentate ligands I have written, right? So bidentate ligand. So please note down, this is very, very important. So this type of compound can exhibit optical activity. So this is called optical isomerism. All these compounds have the ability to rotate the plane of polarized light towards right or left. They can have the ability to form dextroform as well as lavoform. So if the molecule has the ability to rotate the plane of polarized light towards right, it is called dextroform. And if the molecule has the ability to rotate the plane of polarized light towards left, it is called lavoform. Left and right. Left means lavo, day means right means dextro. So the compounds which have octahedral complexes with general formula Ma2B2C2 plus or minus n, Ma2B2CD plus or minus n, Ma2BCDE plus or minus n, where M is called the central metal. M is called what? The central metal atom. And A, B, C, D, E, F are nothing but ligands. And in this A, B, C, D, E, F, at least one should have the bidentate ligand. So the compounds which have octahedral complexes with at least one bidentate ligand having general formula Ma2B2C2 plus or minus n, Ma2B2CD plus or minus n, Ma2BCDE plus or minus n, MABCDEF plus or minus n can exhibit optical activity. These type of compounds can exhibit optical activity. So it's very, very important, children. Please note it down. So this is called optical activity. So now next concept in this. So this is called optical isomerism. So they'll ask which of the compounds will show optical isomerism. So in that type of questions, you need to identify whether they are existing in the form of like this or like this or like this or like this. So total four types. Four types of compound will form will exhibit optical isomerism, and definitely they should contain octahedral complex. First basic condition is the compounds which have octahedral complexes. In geometrical isomerism, the complex can have either octahedral complexes or mostly square planar complex, but optical isomerism purely for octahedral complexes with general formulas compound number 1, 2, 3, and 4. So we need to identify the type of compounds where we can have any of these four. That type of compounds only will show optical isomerism. Will show optical isomerism. They have the ability to rotate the plane of polarized light towards right or left. So the optical isomerism, the molecules are nothing but they are called as chiral molecules, and they are also called as, and dextroform and lavoform are called as enantiomers. Dextroform and lavoform. Dextro and lavoform together they are called as enantiomers. Dextro and lavoform together they are called as enantiomers. And the molecules are nothing but enantiomers. I'll write the spelling properly. Enantiomers. So please note down, children, this is very, very important. You'll not find this type of compounds so in any other book. So that's why we have made it specially for you. So dextroform and diaform will form enantiomers. Together they are called as enantiomers. And these are called chiral molecules. These are called what? Chiral molecules. So chiral molecules will have optical activity. They are non-super mirror images of each other. Non-super mirror images of each other. They will show optical activity when they are kept in a plane of polarized light, that is in polarimeter. They will rotate the plane of polarized light towards right or left. If they rotate the plane of polarized light towards right, it is called dextroform, and if they rotate the plane of polarized light towards left, it is called lavoform. So dextroform and lavoform. So please note down, this type of compounds will show optical activity. So the compound which can show geometrical as well as optical isomerism is Ma2B2C2 plus or minus N, like that in as I showed you, that is platinum dichloro, there is PtCl2. Here I'm writing as there is no space, PtCl2 En taken twice is the compound, a whole to the power of 2 plus is the compound which can show optical activity, as well as the cis isomer of this compound will show optical activity, and this compound can show geometrical isomerism. So the compound which can show both optical as well as geometric means this is the compound. So please note down, children, this type of questions definitely they'll ask in the entrance examination. It's very, very important. Next continuation. So I hope you have written all this concept in your classwork. It's very, very important. Concept 1, concept 2, 3, 4. So which type of molecules will show geometrical isomerism? The compounds which have octahedral, that is the coordination compounds, are the complexes which have octahedral complex structure geometry with general formula Ma2B2C2 plus or minus N, Ma2B2CD plus or minus N, Ma2BCDE plus or minus N, and MABCDEF plus or minus N will show, can exhibit optical activity. That is point number 1. Point number 2, the complex should contain at least one bidentate ligand. That is point number 2. So these are nothing but the complexes which can show optical activity. They can have the potentiality to rotate the plane of polarized light towards right or left. So I hope it is clear. Next continuation. So optical isomers are mirror images that cannot be superimposed on one another. These are called enantiomers. The molecules are ions that cannot be superimposed are called chiral molecules. The two forms, dextro and lavoform, are together. They are called as enantiomers. Are defined depending upon the direction they rotate the plane of polarized light in a polarimeter. Optical isomerism is common in octahedral complexes involving bidentate ligands. Very, very important point. Next example we have shown already. Next example, in a coordination entity of the type PtCl2En taken twice plus 2, only the cis isomer shows optical activity. The trans will not show optical isomerism. So please note down this, children, very, very important. Next we'll move to other topic in this chapter, that is Werner's theory. So let us see now. Theories of bonding in complex compounds. Theories of bonding. So already you know ligands will form coordinate covalent bond. So based on the theories of bonding in complex compounds, many approaches have been put forth to explain the nature of bonding in complex compounds. First, we have Werner's theory. Second, we have valence bond theory. Third, we have crystal field theory. Fourth, we have ligand field theory. And fifth, we have molecular orbital theory. So all these theories are very important. Now in this lecture, we are going to discuss about first theory. After that, we will do questions based on Werner's theory as well as isomerism in coordination complex. So this lecture is very, very important. Please note down. All the points are very, very important. Now let us start now. Werner's theory. So based on the bonding in complex compounds, we have various theories: Werner's theory, valence bond theory, crystal field theory, ligand field theory, and molecular orbital theory. So let us start now all these theories now. So in this lecture, we can do only Werner's theory. After that, we'll do the next session. Next, first attempt to explain bonding and properties of complexes was made by A. Werner. He prepared a series of complexes by combination of he prepared a series of complex compounds by the combination of cobalt, chloride, and ammonia. He studied the conductance properties of the compounds and by the reaction with silver nitrate. Here, the silver nitrate is important. They'll ask this. So first, how could he started the coordination compounds? He could form many complex compounds by the combination of cobalt, chloride, and ammonia. He studied the conductance properties of the compounds and by the reaction with silver nitrate. In order to explain the properties of these compounds, he explained that all six groups, that is chloride or ammonia molecules, should be bonded to the cobalt atom at all times during the reaction. So cobalt has a capacity to form six compounds. So that's why it is all the six groups, that is chloride or ammonia molecules, should be bonded to the cobalt atom at all times during the reaction. He introduced the concept of secondary valency for the metal atom by which the cobalt atom is directly bonded to six groups. The following table gives the observations made by Werner. So it's very, very important. Please note down whatever I underlined. You please concentrate again the same concept as you are seeing the video lecture. So please, you can play the video so many times. That's why we have made the video lectures instead of taking Zoom classes. So now compound here, COCl3 dot 6NH3. This is the cobalt trichloride dot 6NH3. This is the complex compound. The color is yellow in color. Total ions produced in aqueous solutions is 4. White is producing 4, 1 ammonia and 3 chlorines. And total moles of silver chloride produced is 3 because it is nothing but 3 chlorines are there. That's why it can combine with silver and form silver chloride. And solution conductivity corresponds to 1:3 electrolyte because it is producing 3 moles of silver chloride. And the formula of the complex is CONH3 taken 6 times Cl3 outside because this is called the secondary valency because this is electron donor. Chlorine is having electron donor. It is donating electrons to cobalt +3. Cobalt is in +3 states. Chlorine is in -1 state. Next, COCl3 dot 5NH3. Purple color. What color it is? Purple color. And total ions produced in aqueous solution is 1 CO. Here, how we can got 4? Because it is 1 CO plus 3 and 3 Cl minus. So total it is how much? 1 plus 3, 4. In the same way here, 1 CO plus 3 and 2 Cl minus. 2 Cl minus. And that's why it is producing only 2, 3. So next, number of moles of silver chloride produced is 2. And solution conductivity corresponds to 1:2 electrolyte. And this formula of the compound is this, that is CONH3 taken 5 times Cl inside and Cl2 outside. Anyway, cobalt is giving +3 state here also. But the thing is 1 Cl is present inside, 2 Cls will be present outside. Next, we have green color, COCl3.4NH3. They will ask definitely the colors or number of ions produced in silver chloride solution or number of moles of silver chloride produced also they will ask, and the solution corresponds to electricity. Solution conductivity corresponds to also they ask, and they ask also even the formula of the complex. So COCl3.4NH3, green color. The number of ions is only 2 because only 1 Cl is outside, and number of moles of silver chloride produced is 1 because only 1 chlorine is combining with silver. Remaining 2 are coming inside the complex coordination entity, and it is 1:1 electrolyte. The formula of the compound is CONH3 taken 4 times Cl2 dot Cl. So next we have violet color COCl3 dot TNH3. It is only having one species, and number of moles of silver chloride produced zero because all the three chlorines are inside the coordination entity. If one chlorine is outside, it can produce one. Two chlorines outside, it can produce two. Three chlorines outside, it can produce three. And as there is no chlorines produced outside, it is nothing but zero. Number of total moles of silver produced is equal to zero. Definitely, you'll get one question based on this table. So please listen carefully. And the solution conductivity corresponds to zero, no electrolyte, and this is the formula of the complex. So please note down this four. This entire table is important, so please note down in your classwork. Definitely they'll ask either colors, or they can ask number of ions produced in the solution, or they can ask number of moles of silver chloride produced also. Anything they can ask in the examination. So please note down, even they can ask the formula of the complex. The least probabilities electrolytes 1:2, 1:3, like that. First column, second column, these two columns and these three columns. These three columns are important, even four. Total four columns are important. So please note down these four columns, very, very important. We have to remember for the examination, entrance examination. I hope it is clear. Next continuation. Postulates of Wednesday. In coordination compounds, metals show two types of valencies. Every metal will show two types of valencies. First one is primary valency, second is secondary valency. The primary valencies are normally ionizable and variable. So in the previous class, chlorine is the primary valency and ammonia is the secondary valency. It is satisfied by negative ions. The primary valency is the oxidation number of the central atom. As I told you, the primary valency is the oxidation number of the central metal atom. If the metal atom, central metal atom, like in the previous case, we have plus 3, so it has 3 chlorine ions, 3 Cl minus. So both plus and minus will get cancelled. So the primary valency is the nothing but the oxidation number of the central metal atom. So what is the primary valency of this compound? That is COCl3 dot NH3. The primary valency is nothing but plus 3. Why? Because it is the oxygen state of central atom. It is the oxidation number of the central metal atom. So please, very important, very, very important. Please note down. So first postulate, in coordination compounds, metal shows two types of valencies: primary valency, secondary valency. The primary valencies are normally ionizable and variable. It is satisfied by negative ions. So it is satisfied as it is positive, it is satisfied by negative ions. So that's why we can say, in fact, the primary valency is the oxidation number of the central metal atom. Next continuation. The secondary valencies are non-ionizable. They will not flourish ions. They will not produce any ions, and are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number and is fixed for a metal. The secondary valencies are directional in nature. Very, very important. Fourth point, the secondary valencies are directional in nature. The ions or groups bound to the metal are directed in space to give a specific geometry for the complex corresponding to different coordination numbers. So based on the coordination numbers of the metals, we can write the geometry of the molecule. We can write the geometry of the molecule. And Werner's theory observed that these are the regular polyhedrons, which are commonly known as coordination polyhedron. So the secondary valencies are non-ionizable and are satisfied by the neutral molecules or negative ions. The secondary valency is equal to the coordination number and is fixed for metal. So please note down, these are the main postulates of Werner's theory. Definitely you'll get one question based on Werner's theory. All these Werner's theory points are important. Next postulate, he further postulated that octahedral, tetrahedral, and square complexes. As I told you, Werner's theory gave you the shape of the geometry of the molecule, shape or geometry of the molecule, that is octahedral, tetrahedral, and square planar geometrical shapes are common in coordination compounds of transition metals. Thus, CONH3 taken 6 times plus 3, COCl NH3 taken 5 times, and COCl2 NH3 4 times plus are octahedral entities. So these are octahedral entities, while nickel carbonyl compound and platinum tetrachloride are tetrahedral and square planar complex respectively. So this is square planar and this is tetrahedral. So based on Werner's theory, he could successfully explain certain geometries of the coordination entities. So it is very, very important. So it has primary valency, secondary valency, number of ions produced also is very important, and color of the compound, everything he has mentioned it. Next continuation. Limitations, what he could not explain. This theory could not explain why only certain elements possess the remarkable property of forming coordination compounds, why the bonds in coordination compounds have directional properties, and third one, magnetic and optical properties of complexes. So he could not explain the magnetic property as well as optical property. So these are the limitations of Werner's theory. All the three limitations are very important. Why only certain elements possess the remarkable property of forming coordination compound means why only D block elements are forming coordination compounds, that he could not explain. Why only D block elements, that is transition metals, are forming coordination compounds. Why the bonds in coordination compounds have directional properties. He could not explain that the bonds are nothing but coordinate covalent bond, that he could not explain. And third point, magnetic and optical properties of complexes, he could not explain. So he could not explain coordinate covalent bond, coordinate covalent bonds which have directional, because the ligands are giving donor electron pairs to settle metal atom, and due to which they will form coordinate covalent bond. So that's why they are forming, they have directional nature. Covalent bond is directional in nature, as we already know. So, but he could not explain that points in this theory. And the magnetic and optical properties of the complexes also he could not explain. So that's why this theory is failed. But mostly, what are the success achievements of this theory? That is, he could successfully explain about the geometry of complex compounds and primary valency and secondary valency of geometry complex. Sorry, that is complex compounds. Let us see now. So I will share with another slide so that you can add all the shares. Now we will discuss questions based on. Now we will discuss questions based on questions. Very, very important, these questions. Now we are going to discuss all the questions based on MCQs. That is questions based on isomerism as well as Werner's theory. Isomerism and Werner's theory. This lecture is very, very important. As I told you, definitely you'll get one question based on this. So please note it down. Questions based on isomerism and Werner's theory. Let us start now. Question number 1, important MCQs. The following does not give a precipitate either with silver nitrate or barium chloride. First question, the following does not give a precipitate either with silver chloride or barium chloride solution. Sorry, silver nitrate. Here I have written mistake. Is silver nitrate. Option A, it is CONH3 taken 6 times Cl3 outside. CONH3 taken 6 times Cl3 outside. Option B, it is CONH3 taken 5 times CONH3 taken 5 times Cl one side inside and Cl2 outside. And option 3, that is option C, is CONH3 taken 4 times CONH3 taken 4 times Cl2, 1 Cl outside. And option D, it is cobalt NH3, that is hexamine, that is NH3 taken thrice, that is triamine, Cl3 inside. So which type of, with the following does not give a precipitate, the following does not give a precipitate. Just I have written the wrong option here. 1 second, please note down. This is CONH3 taken 3 times Cl3. I'll just write the options again. C1 taken 3 times Cl3 inside and Cl2 is not outside. C1 taken 5 times ClSO4 and this is options I have written wrong. SO4 outside and CONH taken 4 times Cl2 Cl inside. This is correct only. CONH taken 4 times and Cl4 Cl. So this is Cl4 inside and Cl outside. So this is the compound. Now in this, which type of compounds following does not give precipitate either with silver nitrate or with barium chloride solution? So let us see the answer now. It is second option. Solution I'm writing here. So this is based on purely Werner's theory. Solution for this option is second. Why it is second option? That is CONH taken thrice and Cl3 because it cannot ionize to produce free Cl or SO4 2 minus. It cannot ionize. It cannot ionize because all other it can produce SO4 Cl and Cl outside, but the Cl3 inside, so it cannot, since it cannot ionize to produce free chlorine ions, or sulfate ions, or that's all, sulfate ions. So this is the reason why it cannot produce, does not give a precipitate, either with silver nitrate or barium chloride solution, because here it is Cl3 is inside the coordination entity, so it cannot ionize to produce free Cl minus or SO4 2 minus ions. So that is the reason. Very, very important. Question number 1. I hope you clearly understood. Let us see now question number 2 based on Werner's theory. Second question, please note it down. Which of the following has highest molar conductivity? Highest molar conductivity means number of ions. Which can produce more number of ions? It has more molar conductivity, highest molar conductivity. So that is the hint. Which can produce more number of ions, that is more important. So option 1, that is option A. It is CONH3 taken 6 times and Cl3 outside is based on the table which I have given for Werner's theory. Please see the table. CO3 NH3 taken 5 times. CONH3 taken 5 times. 1 Cl inside, 2 Cls outside the coordination entity or the coordination sphere. And third option, CONH3 taken 4 times. Cl2 outside, 1 Cl. And fourth option, CONH3 taken 5 times or 4 times, is 3 times, and Cl3 inside. Very, very important question. So which of the following has highest molar conductivity? Easily you can say the answer. I'll write the solution here. Based on this table, you know, number of ions produced by this compound is number of ions. Answer is option A, because it can produce, option A can produce 4 ions. it can produce 4 ions. Option B, option A produce 4 ions. Option B, as it contains, it is only 3 ions. Option B, only 3 ions, because one inside, two outside. And option C, only 2 ions it will produce. And option B, D, 0 ions. So which can produce more number of ions, that has the highest molar conductivity. So this is based on Werner's theory. So option is A, that is CO energy taken 6 times Cl3. It is yellow in color and it produces 4 ions. It produces how many ions? 4 ions for ionization, 4 ionization ions. So due to which what happens? It has highest molar conductivity. As the more the number of ions, more is the conductivity. More the number of ions, more is the conductivity. More the number of ions produced, more number of ions produced, more the number of ions produced, highest is the conductivity. Higher is the conductivity. Higher is the conductivity in the solution. So please note down this, very, very important. Next question. Question number 3. All the questions are very important, so please note down. Transition metals. Transition metals elements are transition metal elements. I'll write here transition metal elements. Transition metal elements can form complexes readily because option 1, small size of cation. Option 2, large ionic charge. Option 3, vacant d orbitals. It is vacant d orbitals. And now option A, it is first only. Option B, it is second only. Option C, it is 1 and 2. Option D, it is 1, 2 and 3. So the right answer is option D, because transition metal elements can form complexes readily because due to its small size of cation, larger ionic charge, and have vacant d orbitals. So all the three conditions, all the three will enhance the complex compounds, formation of complex compounds. Next question, question number 4. The primary valency, that is the central metal atom of the ion, is satisfied by primary valency of the metal ion is satisfied by option A, neutral molecules. Option B, it is positive ions. This is also it's very simple question, just for our understanding I have given this. Next, option C, it is negative ions. negative ions, and option D, all the above. So the right answer, everyone can tell easily, you can guess easily. What is the right answer? It could be negative ions, because the primary valence of the metal ion is positive. So it is satisfied by negative ions only. It is satisfied by negative ions. So it's very, very simple question. Just for understanding I have given. I hope it is clear. Next continuation. Question number 5. At least 15 to 20 questions I am going to discuss. The best selected questions. Question number 5 now. Optical isomer have option 1, the property of chirality. Option 2, almost identical chemical properties. Almost identical chemical properties. Option 3, almost identical physical properties. Almost identical physical properties. Option 4, all the above. So optical isomers have which of the following properties? Optical isomers have which of the following properties? So they have the property of chirality, they have the almost identical chemical properties, they have almost identical physical properties, all the above. So what is the right option? It could be. So optical isomers have, we already know optical isomers are different towards rotation of plane of polarized light. So they are different because, so that's why their chemical properties and physical properties are not similar. Only they have the property of chirality. They have the property of chirality is similar. Optical isomers have the property of chirality. Remaining all rest is not present. Next question. Question number 6. Number of ionizable and non-ionizable ionizable chlorine ions, Cl minus ions in COCl3 5NH3 respectively are option A, it is 3, 0. Option B, it is 2, 1. Option C, it is 1, 2. And option D, it is 0, 3. So number of ionizable, how many chlorine ions are there and how many, as we know in this complex compound, chlorine is only ionizable, ammonia is neutral ligand, so it is not ionizable. So we can guess the answer easily. You can easily tell the answer. What is the answer? It could be 2, 1. It could be how much? 2, 1, because one chlorine should definitely be inside. So answer is 2, 1. Why it is 2, 1? I'll explain you. Because All the chlorines are not satisfied with cobalt, so the complex can be written best written as CONH3 taken 5 times, Cl inside and outside Cl2. This could be written like this because it has 6 primary valencies. So 6 primary valencies means total 5 plus 1, 6. So one of the chlorine should come inside. Suppose if NH3 taken 6 times is there Cl3 outside, definitely it has 4 ionizable ions. So it has only 2 and 1. So answer is what? This is 2 and this is 1. So number of ionizable and non-ionizable. This is the non-ionizable. The chlorine which is present inside the coordination sphere is non-ionizable. This chlorine is non-ionizable. Non-ionizable. Very, very important this type of questions. Please note down, children. So the number of ionizable and non-ionizable chlorine ions in COCl3.5 NH3. Suppose if they have given COCl3.6 NH3, definitely it should be 3, 0. So number of ionizable, non-ionizable. Ionizable will be outside the square bracket and ionizable and non-ionizable will be inside the square bracket. And this complex can be best written like this only. CONH3 taken 5 times Cl outside Cl2 because cobalt valence is 6. So definitely they should have 6 coordination, 6 numbers in the coordination entity. So NH3 5 and Cl1 total 6 ligands and outside 2 is there. So outside ligands are ionizable and inside ligand are non-ionizable. So inside chlorine is non-ionizable and these two are ionizable. So it can produce 2 ionizable ions as well as 1 non-ionizable ion. Very, very important this type of questions. Please note it down. Next question. Question number 7. Next question, question number 7. I have written it big to understand it better. Silver chloride. Silver chloride. Silver chloride dissolves in excess of ammonia. Dissolves in excess ammonia due to the formation of soluble complex, due to the formation of soluble complex, due to the formation of soluble complex whose formula is option A, it is AgNH3Cl, AgNH3 inside, outside is Cl. Option B, it is AgNH3 taken twice, outside it is Cl. Option C, it is AgNH3 taken thrice, AgNH3 taken thrice, outside Cl. And option D, it is AgNH3 taken 4 times, outside it is 1 Cl. So this is the question. Silver chloride dissolves in excess of ammonia to formation of soluble complex. So answer is, for this answer, the solution I'm writing here. So when silver chloride dissolves in excess of ammonia, silver chloride combines with 2 moles of ammonia and forms AgNH3 taken twice Cl complex. So as it is forming this, the answer could be second option. So these type of questions are very, very important. Please note down. Next question. Next question. Question number 8. Please note down. Which of the following does not exhibit? As I told you, I'll do questions based on Werner's theory and isomerism. Which of the following does not exhibit optical isomerism? Which of the following does not exhibit optical isomerism? So we should identify the general formula of optical isomerism, then only we can answer this type of questions. That's why I have written you clearly. First option, CrNH3 taken thrice, Cl3 outside. Second option, CrEn taken thrice, outside it is Cl3. Third option, that is chromium metal, CrEn taken twice, Cl2, outside it is Cl. And fourth option, CrEn NH3 taken twice, Cl2 inside and Cl outside. So the compound which will exhibit optical isomerism, first, for this I'll write the solution. First, which type of compounds can show optical isomerism? Number one, first condition, they should have octahedral complex. They should have what? Octahedral complexes with at least they should have octahedral complex with at least one bidentate ligand, with at least so I'll just share it off. Please note down. Yes, with at least one bidentate ligand. Bidentate ligand. It is most important. So they should have at least one octahedral complex with at least one bidentate ligand. First option, we don't have any bidentate ligand because NH3 amine is neutral ligand. It is monodentate, and Cl3 is also neutral ligand. So it is negative ligand. So it is also monodentate. Remaining all options we have bidentate ligands. Here 1, here 3, and here 2. But here we don't have bidentate ligand. So octahedral complex, even though it has, but it has no bidentate ligand. So answer is first option. So this type of questions are very, very important. Please note down. Next question. Question number 7. Question number 8 is over. Now question number 9. So I'll write with red pen. Question number 9. Please note down. Coordination compounds. Coordination compounds. Coordination compounds. That is, first compound is platinum triamine. We have NCS. This is thiocyano, and platinum NH3 taken thrice. It is SCN, NCS and SCN. Are examples of dash isomerism. Which type of isomerism they'll exhibit? So it has two SCN, and the donation of ligands to sulfur, donation of ligands to nitrogen is there. So it is nothing but ambidentate ligands. So ambidentate ligands will show which type of isomerism. They show first one coordination isomerism. They have given the option coordination isomerism. Second one ionization isomerism. Ionization isomerism. Third one linkage isomerism. And fourth option we have optical isomerism. So as they are ambident ligands, ambidentate ligands, ambidentate ligands, ambidentate ligands, which have anyway they have two donor atoms, which have two donor atoms shows linkage isomerism. What type of isomerism? They'll show linkage isomerism. Very, very important point. So easily you can understand by seeing the example. So option C. Option C. What is the solution for this? Ambidentate ligands which have two donor atoms like cyanide and isocyanide, like NCS and SCN, which have two donor atoms shows linkage isomerism only. So these two will show the examples of linkage isomerism. Next question. So it is clear. So these type of questions you'll get from isomerism. Next question number 10. Geometrical isomerism is observed in geometrical isomerism. Geometrical isomerism is observed in option A. It is tetrahedral complex. It is very simple question, theoretical. Tetrahedral complex. Option B, it is square planar complex. Square planar complex. Because in the previous lecture we already discussed about questions based on isomerism. That's why I'm discussing both isomerism and Werner's theory in this lecture, as I told you in the starting of the lecture only. So that's why we are giving more number of questions. Next we have linear complex. And finally we have fourth option, planar triangle complex. Planar triangle complex. These are the geometry of the complex they have given. So geometrical isomerism is observed in which type of complexes you already know. So I'll write the statement. By that statement you can understand geometrical isomerism is observed in square planar complex as well as octahedral complexes. And optical isomerism is observed only in octahedral complexes. So answer is, by seeing this statement easily you can guess the answer. So geometrical isomerism is observed only in square planar complex as well as in octahedral complexes. So answer is B option. Second option, that is B, option B. It is clear? Next question. Next question now. So trying to giving you the best possible questions. Next question. Question number 11, I believe. So let us see the previous slide. So it could be question number 12 or 11. So let us see. The complexes CO NH2 taken 6 times, Cr C2O4 taken 3 times, that is oxalate ion taken 3 times, and CrNH3 taken 6 times, and C2O4 taken, sorry, C2O4 taken 3 times. C2O4 taken 3 times shows or exhibit option A, geometrical isomerism, option B, ionization isomerism, option C, link coordination isomerism, and option D, linkage isomerism. So what is the answer? It could be easily, you can easily understand. So it is nothing but which type of isomerism it exhibit? Coordination isomerism, because coordination means the ligands will change. So here in this case, NH3 is coming this side and C2. So exchange of ligands takes place. So that is nothing but coordination isomerism. In coordination isomerism, exchange of ligands takes place. Interchange or exchange of ligands takes place. Exchange or interchange of ligands takes place. So here the ligands are taking place. So in the first case, cobalt is having ammonia and chromium is having oxalate ions. In the second case, chromium is having ammonia and cobalt is having oxalate ions. So that's why exchange of ligands takes place. I hope it is clear. Next question number 13. Next question, I'll write it. So it is a lengthy question, so I'll take a new slide. So this is question number 12. Next question number 13. CO NH3 taken 4 times. This question is very, very important. As I told you, I'll discuss about isomerisms. NO2 taken twice. NO2 taken twice. And Cl outside. Cl outside exhibits option A, linkage, comma, ionization, and next we have geometrical. That is the first option, that is option A, geometrical isomerism. So you should think about clearly. It can exhibit linkage, ionization, and geometrical isomerism. Option B, ionization, comma, geometrical, and optical isomerism. All the things should satisfy. So optical isomerism. Next, third option, linkage, comma, geometrical, and linkage, geometrical, and optical isomerism. And fourth option, we have linkage, ionization, and optical isomerism. So these are the 4 options we have. out of which we have to select only one option. And now carefully observe the structure, cobalt. So what is the name of this compound? So nitrogen two times are there, so nitrito N twice. So dinitro, so here tetraamine. So tetraamine, tetraamine, monochloro, dinitrito N, cobalt 3. Cobalt 3. So this is the compound name, and this type of compound will show which type of isomerism we have to check now. So first we'll see this is a molecule of type Ma4B2 M. I'll write the solution here. So it is a molecule of type Ma4B2 plus or minus N. So it is here plus or minus N. So definitely it will show geometrical. It will show what type of isomerism? Geometrical. And linkage also, NO2 can go outside, Cl can come inside. So it can have linkage isomerism. And third one, it has ionization isomerism, because ions also it can form Cl minus ions as well as NO2 minus ions. So ionization. How it can ionization isomerism? One NO2 if you keep outside, it will form ionization isomerism. So ionization isomerism, it will show linkage isomerism, it will show geometrical isomerism. Let us see now. I'll write the example here. For linkage, you can say NO2 will come inside, Cl will go, sorry, NO2 will come outside, Cl2 will go inside. So this is linkage, which you can write like this: CO, NH3 taken 4 times. Anyway, neutral ligand will not disturb. Cl inside and outside. Donor atoms can be from NO2 taken 2 times. Whereas here ionization, it can have CO, NH3, NO2 inside one, outside one also you can write. Outside NO2 dot Cl. Dot Cl. We can write like this. So this is linkage, coordination, and geometrical is the type Ma4B2. So it will show geometrical also. So it is very, very important. Answer is linkage, ionization, and geometrical isomerism. Option A. First option. These type of questions are most important. Definitely they are going to ask this type of questions in JEE mains and NEET also. So we have to guess by seeing the compound, which what this compound can exhibit what type of isomerisms. Very, very important. Next question, question number 14. Question number 14. Which are the following? Which of the following is an example of coordination isomerism? Coordination, actually no hyphen should be kept, simply I kept for understanding. Coordination isomerism. So these are direct question. This type of questions are also important. Option 1, CONH3, CONH3, Br inside, that is bromine, and sulfate outside, and CONH3, sulfate inside and Br outside. That is option A. Option B, CONH3 taken 5 times, so this NH3 taken 5 times, NH3 taken 5 times. Option B, CONH3 taken 5 times, NO2, Cl2 outside, and CONH3 taken 5 times, CONH3 taken 5 times, ONO, and Cl2 outside. Next option C, Cr, H2O taken 6 times, that is aqua, hexa aqua, Cl3 outside, and Cr H2O taken 5 times, Cl inside, Cl2 outside the coordination sphere, dot H2O. Next, fourth option, Cr NH3 taken 6 times, cobalt cyanide hexa 6 times, hexacyano, and CO NH3 taken 6 times, and CrCN taken 6 times. So by seeing the example, easily we can understand. So what is the answer? It could be, please guess it out. Please answer, try to understand. So this is nothing but what? This is an example of linkage isomerism, because sulfate, the donor atom is from sulfur. This is bromine. So this is nothing but linkage isomerism. This is also NO2Cl2 outside, ONO. This is nitrito N and this is nitrito O. This is also linkage. Third one, it has no isomerism. And this third one is hydrated isomerism. Third one is what? So first one is linkage. Second one is also linkage. Third one is hydrated isomerism. And fourth one is coordination isomerism. So answer is fourth option, coordination isomerism. So first one linkage, second one also linkage, third one is hydrated isomerism because one water molecule has come out, and fourth one is coordination isomerism. So all the examples have been given. So please note down, this is fourth option, very, very important, this type of questions. Next question, we'll proceed to next question. Question number 15. All these questions are most important. That's why we are giving it now for you, for your better understanding. Very important question next. Which of the following compounds following compounds show optical isomerism? Optical isomerism. Which of the following compound shows optical isomerism? Now, option A, it is Cr C2O4 taken thrice 3 plus. Option B, it is CO Cn taken 6 times whole to the power of 3 minus. So this is also 3 minus. I'll just rub it. First one also 3 minus, second one also 3 minus. Third option, Cu NH3 taken 4 times whole to the power of 2 plus. And fourth option, ZnCl4 2 minus. ZnCl4 2 minus. It's very simple question and it's important also. So I'll write the solution. By this time we may get the answer. First condition, the solution for this, to exhibit optical isomerism, it should have at least one bidentate ligand. To exhibit optical isomerism, the complex should have at least, it can be more than, but at least one bidentate ligand. So first option only we have bidentate ligand, that is oxalate ion. Oxalate ions, it is bidentate because it is nothing but C2O4 2 minus. So oxalate ion is bidentate. Remaining all we have monodentate, this is neutral monodentate, and this is monodentate. So directly, easily we can see without octahedral complex directly we can say To exhibit optical isomerism, the complex should have at least one bidentate ligand, and it should have and it should have octahedral geometry. Octahedral geometry. These are the two conditions. Please don't forget this condition. If the complex is having octahedral geometry and it contains at least one bidentate ligand, it will exhibit optical isomerism. It will exhibit what? Optical isomerism. So this condition is very, very important. So please note down. Next question. Question number 16. So Warner's theory and optical isomerism, we are doing the best possible questions. Now, let us see the type of hybridization shown by the type of hybridization shown by cobalt NH3, that is amine taken 4 times, Cl2, no, it is Br2 and Cl outside is option A, optical and ionization. Option B, it is geometrical and optical. Geometrical and optical isomerism is hybridization, no isomerism, sorry. I don't know why I done hybridization. It is isomerism. The type of isomerism shown by geometrical and optical. Option C, geometrical and ionization. And option 4, it is only geometrical. So let us go to the solution for this question. They are given the molecule tetraamine dibromo monochloro cobalt 3. So this is a complex. This is an anionic complex. So cobalt 3. The name of this compound is tetraamine dibromo monochloro. That is chlorido cobaltate 3. Cobaltate 3. Oxygen state of cobalt is plus 3. So easily we can understand by this name. And the type of isomerism is shown by, it is nothing but optical. It is ruled out because it has no bidentate ligand. As this complex does not involve any bidentate ligand, because this is ammonia is neutral and it is monodentate ligand. Bromine is negative ion, but it is monodentate. Apart from this, chlorine is also monodentate. So there is no bidentate ligand. So optical is ruled out. So first option is wrong. Second option is wrong. And third option we have geometrical and ionization. So as it can show ionization, because Br2 can taken as BrCl outside. This can be written as CO NH3 taken 4 times Cl Br2. So Br2 can go outside also. So it can form ionization, and this is a molecule of type Ma4B2. Ma4B2 will show geometrical isomerism. So GI geometrical isomerism. So answer is geometrical as well as ionization. So this explanation is clear. Very, very important. You need to see the possible outcomes. So ionization, it is compulsory because we know chlorine can come inside and bromine can go outside. So ionization, it can form 2 bromine ions and can form more 1 bromine chlorine ion. So it will show definitely ionization isomerism, but we have to check whether it will show geometrical isomerism. I have given you the types of isomers, the types of compound which can show geometrical isomerism. In that, we have this Ma4B2 plus or minus we have. So this is Ma4B2 geometrical isomerism. So answer is geometrical as well as ionization. Geometrical as well as ionization. So these type of questions are very important. So please note down. Very, very important. I think you understood this answer. Next question. Which of the following? Question number 16 or 17, whatever the number it could be. Which of the following? Which of the following does not have optical isomerism? Does not have optical isomers is the question. Option A, it is cobalt En taken thrice Cl3 outside. So it has one bidentate ligand. So definitely it will have optical isomerism. Option B, CO NH3 taken thrice Cl3 inside. And option C, CO En taken twice Cl2 and Cl outside. And option D, CO En NH3 taken twice Cl2 and Cl. So these are the options we have. So which of the following does not have optical isomers? Very, very important this question. Basically, we have the idea that they should have at least one bidentate ligand, or else the coordination number should be 6. Coordination number should be 6. Here it is 3 bidentate ligands. Here no bidentate, but the coordination number is 6 because 3 plus 3 is 6. And here the coordination number is 2 plus 2, 4, 4 plus 6 plus 1, 7 it is coming. And here it is 2, 4, 6. Inside the bracket itself it is 6. And inside the bracket should not be more than 6 or less than 6. So here the coordination, the solution I'll write here, solution for optical isomerism, the coordination entity, the coordination number should be 6. The coordination number should be 6, or it should contain bidentate ligands. Or it should contain, no need, right? So simply write the coordination number is 6. If it is less than 6, it will not show, even though it doesn't contain bidentate ligands. Even though it contains bidentate ligands also, the minimum first is the coordination number should be 6. And here if you take 2 plus 2, 4, here it is 6, here it is 3 plus 3, 6, and here it is 2, 4, 6. So answer is definitely option C. Option C, even though it contains 2 bidentate ligands, is 2 plus 2, 4, 4 plus 2, 6. I don't think it is C. It should be 2 to the 4, 4 plus 2, 6. No, it is not correct. 14th one. So this is question number 16. Second option. That's what I'm discussing. This is wrong. Second option is right because it should have contained coordination number is 6, but it should be containing one bidentate ligand. No bidentate ligand. Bidentate ligand. Best is bidentate ligand should contain. So no bidentate ligand because chlorine is monodentate, ammonia is also monodentate. So answer is second option. Next question. So these are the different types of questions we are getting from isomerism as well as Werner's theory. Now let us see next question now. Very, very important next question. Which one of the following has, very, very important, this question has come for previous JEE Mains 2010 question. Which one of the following has That's why I'm discussing so many questions, because this from this area definitely you'll get one JE means question. Neat. That's why I'm discussing more questions. So please try to understand. Has an optical isomerism. Has an optical isomer. This is JE means 2010 question. Please note it down. So you can see in the previous competitive questions. Option 1, it is zinc, En taken twice, that is ethylene diamine taken twice, 2 plus. Option 2, it is zinc, En taken twice, NH3 taken twice, 2 plus. Option C, that is option 3, cobalt, En taken thrice, 3 plus. That easily can tell the answer. And option 4, it is cobalt, water, water taken 4 times, ethylene diamine 1 time, and whole 3 plus. So this is the question we have. Now we have to check the answer now for this. So easily you can tell the option is 3. Why? Because it has 3 bidentate ligands. So I'm writing the solution now. So option is 3 because it has 3 bidentate ligands. Easily you can understand. 3 has unsymmetrical octahedral structure. So it has unsymmetrical octahedral structure. It has unsymmetrical octahedral structure. So it can exhibit optical isomerism. Octahedral structure. Anyway, moreover, we have given the example also for octahedral structure. So that's why this is the question for JE means 2010. So please note down this type of questions you will get in the examination. Next question. Question number 18 or 19, whatever it is, don't see the number. Next question. Which are the following? The correct statement. This is also important question. The correct statement. The correct statement on the isomerism, on the isomerism associated with the following complex ions. With the following complex, following complex ions. So see the question now. Option A, nickel, H2O taken 6 times or 5 times. This 5 times. NH3, outside it is 2 plus. Yes. Option B, nickel, H2O taken 4 times. NH3 taken 2 times. Complex charge is 2 plus. And option C, it is not option, these are the conditions they are given. Nickel, H2O taken 3 times, NH3 taken 3 times, and it is plus 2. So options now, first option, A and B shows only geometrical isomerism. Geometrical isomerism. Next, option B, that is option second option. A and B show geometrical and optical isomerism. Geometrical and optical isomerism. Next, third option. B and C show B and C show geometrical and optical. And optical isomerism. And fourth option, we have B and C show only geometrical isomerism. So it is purely based upon geometrical and optical. So we need to check properly. Anyway, they will not show optical isomerism because they do not have bidentate ligands. Point number one. This is straight JE means question 2016. So I'll write here JE means 2016. Online exam, JE means 2016. You can see the previous question paper. You definitely will find this question. So the color statement on the isomerism associated with the following complex ions: nickel, penta-aqua, amine, and nickel, tetra-aqua, diamine, like that they are given. So they are given all the three complex, they have given three complex compounds, and you need to identify which type of isomerism it will show. It's very, very important question. So B and C show what type of isomerism it can show. We can identify that thing. So it is of the form B and C. B and C is what type of molecule it is. I'll just write here. So definitely it will not show optical. So it will show only geometrical. So, but which will show geometrical, that we have to see either A and B will show or B and C. Because why no optical? No optical because as the molecule does not contain bidentate ligand, it will not show optical isomerism. Since the molecule does not contain bidentate ligand, here no bidentate ligands are present in these compounds. So definitely it will not show optical isomerism. They will show only geometrical isomerism. But which type of molecules will show geometrical isomerism? You can see here. So this is of the type MA4B2. And this is of the type MA3B3. Complex type MA3B3. These are the complex type MA4B2. So you can easily search in the compounds which show geometrical isomerism. And this is of the type MA5B. MA5B. So which type of compounds will show geometrical isomerism? B and C. So answer is B and C shows only geometrical isomerism. So answer is fourth option. They will show only geometrical isomerism. Fourth option is the right answer. Please note it down. These type of questions are very important. This question has come for JE Mains 2016. You can check the previous questions easily. You can understand. So it is previous JE Mains question 2016. So these are the types of questions which we are going to discuss. So we have done enough questions based on isomerism as well as this thing, that is Werner's theory. So next session we'll come up with a new topic. So with this, I'm ending this session. So please follow what we have discussed so far. It's very, very important. Thank you all.